I was thinking like. So guys, today's lesson there will be some overlap from what I've already talked about. I kind of given away some of like the definition of the derivative. I already gave it to you. What is the definition of the derivative? Yes. And what is it algebraic? So it's the slope of the tangent line of the curve. What is it algebraic? Difference quotient would be not just the difference quotient, but with the limit as h approaches 0 of the difference. Okay, so when we talk about some of this stuff, I think we could probably you could write that statement. The derivative is geometrically the slope of the tangent line. If that is not ingrained in your brain already, you could jot that down. And secondly, it's the limit as h approaches 0. We'll write that down. The difference quotient, f of x plus h minus f of x all over h. And we looked at different versions of that in our introduction the other day. We saw for the first time one of the symbols, or actually two of them, for the derivative. There are multiple symbols used for the derivative. That is the definition of the derivative, one of them. So at this point, aside from what I added yesterday, I showed you could find the derivative at a point, if it exists, of a function with the calculator. So you have that. And the truth is you can do that for any of these rules we're going to be learning for differentiation. But we need to know the rules. There's certain functions that we find derivatives of frequently. It's all the functions you've been studying all the way through. It's the polynomial function. X squared, x cubed. It's the rational functions of 1 over x. Sine and cosine functions. Exponential functions, e to the x. We'll learn rules for quickly and easily find the derivative of each of those, and different compositions of those functions as well as combinations. So let's just talk about how we would, at this point, find the derivative of y equals x cubed. I don't know that we'll do it. We've done this enough. How would you find? What would be the first line of the setup for finding the derivative at this point of y equals x cubed? We'd have limit as h approaches 0. And what would it look like this time? For this specific function, how does this translate? And let's skip the f of x plus h part. Let's go right to plugging in the appropriate thing for x in the function. So we would start with if we were evaluating, if we were finding the derivative at x equals 0, 0 would go in there. But if I'm doing this in general, and we did it for a, x, it doesn't matter, let's just do it for x. So if I'm doing this in general for x, it would just take x plus h and I would plug it in right here. I think we'll go ahead and just do the whole thing. So minus, so it'd be x plus h cubed minus x cubed, yeah, all over h. And we've done this one before. It's a bit of work because it's a cubic binomial. You remember the coefficients of the cubic binomial from Pascal's triangle? It's going to be the next row below 1, 2, 1.
1, 2, 4, 3, 1.
No, let's write it. So we got Pascal's triangle is 1, and then we've got 1, 1, and then 1, 2, 1, and then 1, 3, 3, 1. So this is the cubic line. Good. So we've got, let's go ahead and keep going here. Let's do the next step, and then I'm going to let you finish it. Limit as h approaches 0. So we've got 1, and what's the power on x? Cubed. So we've got 1x cubed plus 3x squared h plus 3xh plus oh, so there should be a squared in here. H squared plus, what's the, yes, h cubed is the fourth term. Remember, there are unwritten ones. There's our 1, 3, 3, 1. The powers on the x's go down and then phase out. It's x to the 0, which is 1. So it goes x cubed, x squared, x to the first, and then x to the 0, which is 1. And then h is not in this one. It's h to the 0 at that point. Then h to the first, h to the second, h to the third. And then I've got minus x to the third, which is just this guy right here, all over h. Go ahead and finish simplifying that, please, on your own. You're going to finish simplifying that. And tell me what the derivative of y equals x cubed is in terms of x. Your answer should be a function in terms of x at the end. Hoping we can see here what's happening in terms of like one of the h's cancels out here, but each of the other terms still has an h in it. Any of the terms with h's in it, they go away, right? When I apply the limit as h approaches 0, they're gone. So what's left? 3x squared is left. Okay, write that down here. So what I'm writing in red is the derivative of y equals x cubed. Interesting. What do you notice about that derivative in comparison, the relationship to the original function? It's 1 degree lower. Anything else you notice? A coefficient is, let's say that again?
The leading coefficient is the power of the original function.
Interesting. The leading coefficient is the power of the original function. Interesting. Let's do another example. Man, I don't know. Maybe you guys are ready. Okay, yesterday we talked about one of the symbols of the derivative. This is, as they go through in the textbook, and I've done this before, even with different notes. These are newer notes that I took from my summer lesson. I'm kind of taking some of the notes from our summer lesson and altering them and adding in some of the stuff I've had in the past, and mixing them, making them better. Hopefully, was the whole goal of going this summer. But as they go through in the textbook, when you're doing problems and they're asking for the derivative just for fun or just to help you learn the different symbols, they switch them up a lot. So here's one of the symbols, dy dx. It's nice to see it like this, written like this. So dy dx equals, and we're trying to find dy dx. Do you have a guess as to what dy, so you could do it this way using the definition, okay? And they're going to ask you to do that in the assignment a little bit more. We're almost phased out of that because you just figured out what's called the power rule, some of you think. But so going back to the last chapter, remember with continuity, it's like if this function is continuous and this one is continuous, we can go ahead and add them together, right? Or scalar multiplication works, etc. Same thing with differentiation. So using what you learned, could you tell me, just looking at the 3x squared, what you think the derivative of that part might be? 6x. Yeah, 2x is a good guess. So 6x is another one. Do you see why you might have gotten 6x? So the 2 is coming out in front because there's already a scalar multiple of 3 out here. 2 times 3 is 6. And then how'd you guys know x? Drop down. So yeah. So we have 6x here, and then this is a nice continuous function, and a nice continuous function. They end up being differentiable, both of them. So what do you think the derivative of just 2x might be, just based on what you observed? Just 2? Okay. Okay. Why? Why 2?
Because there's really a 1 there.
There's an unwritten 1 here.
And
You bring that out in front, multiply it by
1,
2,
2, yeah.
1 times 2, and then what do you do with the power?
It becomes 0.
Okay, and then x to the 0 is 1. Okay. And you're correct. This is the derivative, using what's called the power rule combined with those rules of being able to combine things that are differentiable. Okay, so there it is, and that's dy dx. Another symbol we might use is y prime equals 6x plus 2. That's another symbol we use, is that prime. As I talked about yesterday, we called it f prime of x. So this is called y prime. You might want to just jot this down. Y prime is the way we say that. Y prime. And this dy dx, that's how we say that. It's dy dx. I don't know how I really wrote that, but dy dx. And those d's came from that delta, the triangle. It just means change in y over change in x. Because a derivative is a rate of change, like the instantaneous rate of change at a point, which is the slope of the tangent line of the curve. So all these different things, a lot. But, so those are a couple different symbols. I'll show you some other ways to get to it. Any questions on that? So get good. You're getting there. Actually, you could do these now. Forget those today. I may end up having you practice a little bit before. All right, so moving on here. Derivatives exist for functions besides polynomials as long as the curves are, what would you guess here? What do you think needs to be true about these curves for the derivative to exist? They need to be continuous, at least. There will be some problem points. I think we saw it with that square root of x function. If we look at the derivative, I think we did, square root of x. So if you think about y equals, I think I have an example here. Yes, there it is. When you think about the square root of x,
When it like goes straight down.
yes, when it goes straight down, we have what's called a vertical tangent. You can go back to your algebra experience. What's the slope of a vertical line? It's undefined. So there's where our problem lies, is that derivative is slope of the tangent line. Well, if square root of x goes vertical at x equals 0, then you can't get the derivative there, would be the idea. Or there are other places you can have we're going to see that you can have a continuous function, and that doesn't guarantee that you can find the derivative there. But at least it needs to be continuous. That's a starting point. And then we say and differentiable, and there are places at which the derivative of a continuous function will fail to exist. One of them is a vertical tangent. That's one that we've seen. And it says find d dx of the square root of x. Let's see if we can't apply. So we've done this one using the definition, and you will be asked in this assignment to do this with the definition as well. But let's do this with what we've learned. You think we could apply that, what I labeled the power rule that we discovered to this function? How could you rewrite square root of x so that there's a power represented in it? Okay. So I have here, this is equivalent to, oh, and by the way, this is another way of writing the derivative. What did we replace the y with? The actual function, okay? We're asking for d root x of dx. So it's the derivative of square root of x with respect to x. I think we should write that down. Find derivative of square root of x with respect to x. Now, this is so much nicer than it all out. I'm glad you guys can come along for that. This is way better. Because before when we did this, we did square root of x plus h, we did limit as h approaches 0, square root of x plus h minus square root of x over h. You've done that before. You did it last year, you've done it this year already. And then we had to use a little conjugate rule and rewrite it. Made you think, right? But watch this. This is equivalent to dx of x to the 1/2 power. Do you think that rule would apply even if the power is fraction? Probably, yeah, as long as you know the function's defined there. So we'll have to kind of be a little bit careful. But here's what we do: take that 1/2, move it out in front. Right? So 1/2 moves out in front. Write down the x, and then what's going to happen to the power? It is. It's if I subtract 1 from 1/2, where do I land? Negative 1/2. Is it okay to have a negative 1/2 column? Yeah. Sure. Now let me rewrite this one more time to show you why we have a problem when x equals 0 with the derivative. So this is equal to 1 over 2 times the square root of x. Would you agree? X to the negative 1/2, we would move the x down to the bottom, make it positive 1/2. But 1/2 power is the same as square root of x. So lots of recall in algebra. I mean, this is serious algebra. We're doing it pretty. So ask any questions you need on. Don't worry about it. I'm totally fine. I did it. If you're not seeing what's happening algebraically, you should ask. So are we okay with that? Moving it down. So do you see why there's a problem at x equals 0 with the derivative of the original function square root of x? It's not defined. So the derivative exists everywhere except where it essentially goes vertical, which is right at x equals 0. Well, I should say everywhere on its domain, right? So for x greater than 0, you can find the derivative. But continuity is important for the derivative to have a chance of existing, and there's more to it. Okay? There are places where the derivative fails to exist. One is a vertical tangent. What is the derivative with respect to x of f of x equals 1 over x minus 2? We don't have any way to apply what we just learned on the power rule to this guy. So this one, what would our setup be in that? We're not going to do it, but what would our setup be for this guy? We've done this one actually before. The limit, let's see if we can get it here, as h approaches 0 of, you know what it looks like? 1 over x plus h minus 2 minus 1 over x minus 2 all over h. Now maybe I should give you a moment to try this for practice. They're going to ask you to do something like this in the assignment. Maybe we should, I think we should, maybe we should do it. Sorry, I would say. I'm going to let you do it. Exercise left to the reader. Let's go ahead and do it now. So try this one, please. And let's see what we get for the derivative of this rational function in terms of x. So your answer will be another function in terms of x. So go ahead and try this, and then we'll write down the answer. You need any help on that? So yeah, I mean, that's our first step right there. There's no getting around that. But it does simplify out. It's okay. It's okay. It's not bad. Things cancel, and I would leave the bottom as just x plus h minus 2 times x minus 2. I would not distribute that. I would not recommend that because Here's why. You are in the end going to plug in 0 for h, and you're going to have 2x minus 2's, which will become x minus 2 squared on the bottom. That's part of the correct derivative. So keep working on this. Keep going. You can get it. Give it away here. H's cancel. You end up with a 0 in here. So you've got the derivative is negative 1 over x minus 2 squared. And so, you know, some who finished this already are thinking about is that, you know, what's the shortcut on this? Can you think of it? We'll learn one eventually. So there it is. That's the derivative. And so what would this boxed function do from, like, how would I use it in relationship to the original function, the 1 over x minus 2? What would I do? What would it tell me here?
Slope the tangent line of specific.
Yeah, so if I plug in 0 here, which is okay, plug in 0, it would tell me when x equals 0 what the slope of the tangent line of the 1 over x minus 2 function is at that point. Okay, so that's change. So, any questions on that? Do you feel like you could do the algebra for this one? You need to be able to do that. All right. Moving right along. So what does the derivative do? There's some things that the derivative does. It will give us the slope of the tangent line if it exists. You guys said that it seems like functions have to be continuous to have a derivative. Here's an example of a continuous function. Okay, we saw one already. Square root of x is at least continuous on its domain, x greater than or equal to 0, but we found out that square root of x does not have a derivative at 0. It's a vertical tangent. So that's one way a continuous function, at least on its domain, will fail to have a derivative. Here's another one. Sketch the graph of y equals root x, or at least think about it. Sketch the graph of y equals root x. Absolute value. It's not root x, sorry. Absolute value of x. Sketch that graph. Y equals absolute value of x. I want to ask you some questions. What is the slope for x less than 0? Negative 1. So what would the derivative be for x less than 0 of this function? Negative 1. It's just the slope of the tangent line. What would it be for x greater than 0? 1. Notice I didn't ask what is the slope for x equal to 0. Could you tell me? Is it really? Does the curve actually have a tangent line whose slope could be 0 right here? No, it's like it goes from negative 1 slope to positive 1 slope at an instant. In other words, the derivative on the left is, this is going to sound familiar, it's on the test here, it's continuity. Derivative on the left was negative 1. Derivative on the right of x equals 0 was 1. That's a problem. Just like with the continuity, you have a function whose limit from the left is, well, I don't know, it was like negative 2, and on the right is positive 3. Then the function is not continuous because the one-sided limits differ. Same thing applies for derivatives. Okay, same thing applies for derivatives. If I have a derivative on the left of x equals 0 that is negative 1, and on the right is 1, the derivative does not exist at x equals 0. So you may need to write that down. So let's see. Sketch a graph. What is the slope? This is negative 1. And here it's 1. Derivative at this point does not exist. It's actually called a corner. So we have a vertical tangent and a corner. So continuous functions on their domain can not have a derivative at a corner or a vertical tangent. Okay, so let's write that down. So right here, no derivative. The derivative does not exist at x equals 0 because, what's the case here? Because it's a corner, you could say that. But that's fine. We're going to learn that it's a corner. If we were going to be a little more explicit, we'd say the derivative on the left does not equal the derivative on the right. So the one-sided derivatives differ. You can say that.
And we're talking about those derivatives like infinitesimally small or close to zero, right?
Yes. Yep. Because the left and right and derivatives differ. Now, this is very conceptual. There's a problem in the assignment from the textbook. Well, actually, now I'm thinking, I think they're linear functions. So you can actually take this approach with it. But what if, hey guys, what if you couldn't just look at this graph and tell me the derivative on the left is -1 and the derivative on the right is 1? What would you have to do to demonstrate that the left and right-hand derivatives differ and therefore the derivative does not exist at that point? You might.
The derivative of fx plus h and derivative of fx minus h.
Yes. You would have to do the difference quotient for each different function, you know.
Oh, is that what no.
So look at this. You can't plug in that point because that's the problem point. But
You can find the derivative function, and then you can plug in negative one. Oh,
yeah.
They don't need to.
Yeah, that's true. So, but I believe the one that I asked you, like, there's one like this in the assignment, but they're both linear functions. And so all you're doing is you're looking at m on the left and m on the right and noticing, oh, they don't match. So therefore,
There's no derivatives going out there, but right-hand derivatives don't match.
at that point they will.
Oh, at that point.
Yeah, and h is an arbitrarily small number, so yeah. So probably there's no problem. Because think about it, x equals 0, right? What's the derivative or slope of the tangent line x equals 0? It's 0, so we're good. Those are fine. But vertical tangent or corner, the derivative fails to exist at that point. It exists everywhere else in this function. You just told me what it was everywhere else.
Is it because it's linear on each side, or like, why is it different than forever?
Because it is, yeah, because it's a corner. And because it's linear on each side, it becomes a corner. So anytime you have two lines coming together at a point, they're going to have, the derivative's not going to exist at that point because it's a corner. And you could say because it's a corner, that's sometimes sufficient. But if they ask you to explain further. All right, here's another one. This one here. Sketch the graph of y equals x squared is what we were just talking about. Sketch the graph of y equals x squared. So we'll do that just real quickly. You might want to draw a quick sketch. And this time, we can answer the question, what is the slope at the lowest point? Okay, I can draw in a tangent line, a little tangent line here. I'll do it in a different color. Right here, that's the lowest point. And the slope there is actually defined. It's m equals 0. So how does the slope change as x gets bigger? What's happening to that slope as it goes to the right? It's getting closer to vertical. Does it ever go vertical? No. No. So the derivative is defined everywhere there. So it increases, or I like, now like I said, it approaches vertical but never gets there. So the conclusion here, and you could do the same thing on the other side, vertical but never gets there. And we just know that. Why? Pretty much.
This domain is all real.
Yeah, it is. We know that because like y equals x squared is a buddy at this point. We just know that, right? Yeah. So the domain is all real numbers. Right? It doesn't have any vertical asymptotes. So it just keeps going. So it approaches vertical but never gets there. So the conclusion is the derivative exists for all real numbers. And what's the derivative of this? 2x, yeah. 2x is the derivative exists.
So we plus or minus 2x?
Nope, just 2x.
Oh, because we put
There you go. So derivative exists for all those numbers, yeah. Okay? So I'll give you a minute to jot down what you think is important from that. So. Any other questions so far? We saw square root of x, the derivative existed everywhere except at x equals 0. We saw absolute value of x, it existed everywhere except x equals 0 for a different reason. And then y equals x squared, the derivative exists everywhere. And you could tell me what it is, it's 2x. Notice I didn't ask you to algebraically calculate with the difference quotient the derivative of absolute value of x. Kind of a two-part deal. It's probably better just to visually look at it and tell me the absolute value. All right. I'm going to do geometry. So what else here? We got sketch graph of y equals x cubed minus 4x. We're going to talk about the derivative of this guy too. So this is x cubed minus 4x. What does that look like? You know? Do you think you could find the zeros of this? I'd like to be a little more specific just for practice. No, without your graphing calculator. That's awesome. You can use your graphing calculator to find it.
It's between 0 to
Yeah.
Okay.
Is it?
Okay. How'd you get that?
I factored it.
Okay.
Just some weird stuff.
So we set 0 in place of y is equal to, we think of this as pull out an x, and you're left with x squared minus 4. And so it's x plus 2, x minus 2. So the zeros are 0, negative 2, and positive 2. Okay, this goes back to last year too. Parent graph, which way is it going? Like, as I go from left to right, what's happening here? Is it coming down from the bottom? Okay. Coming down from the bottom. Otherwise, if it were negative in front, we'd flip it. It's coming down, and then we won't be too specific here. Comes down, and then it comes down here, and then something like that. Not a sine function. This one might look a little bit like one, but that's a cubic function. So there's our graph of it. We've got some questions here to consider. What is the slope at the lowest point? Lowest.
Well, it doesn't have a low. What would that be?
It doesn't. It doesn't. Okay, so what is it approaching as it gets towards its lowest point? Okay, but what's the slope?
Oh, it approaches vertical.
It approaches a positive vertical slope, yeah. Another question here. What is the slope at the highest point? Same. Very close to vertical, yeah. What about if you were to think about what the graph of y prime could look like? Now, there are a couple of key points here. So the fact that it approaches a really steep positive slope, both as it goes down to negative, as x goes to negative thing, as x goes to positive thing, can help us in thinking about what the y prime is, again, the derivative of this guy. But there's a couple of things here. We've got, at least according to my picture, I don't know how accurate, let's see, if I plug in -1 here, it's -1 plus 4, it's about 3, so I'm pretty close. It's pretty close. It's not too far off. But we've got some points here, right here, at x equals, let's see here, you're right about there. I want a different color. Maybe at x equals -1, and then at x equals +1, maybe around there. This is just we're just sketching it. Right? I have some places where the slope of the tangent line, or y prime, would equal what? Like these reds, 0. Okay, so when I think about what does the picture of y prime look like, I've got a couple places where I know that the slope is 0. So here's what you have to do, and this is very new, this is hard. We're just getting into this now. Is based on the graph of f of x, or of y, what does f prime, or y prime, look like? So we know a couple things here. We know if I draw y prime in red here, is that it's going to go through. I should probably do this on another graph, because what's my scale? I've got x versus, if I'm drawing y prime, it's not y, it's versus slope. Okay, so let's draw, let's do that, because I think it might be too confusing to get right on here. And then we'll overlay it on here, just to get a picture of it. So draw an XY grid, maybe right underneath this one. Oh, it's not XY, it's X slope. So draw an X slope grid, and just keep in mind slope is Y prime or whatever. But so we're graphing X versus slopes. So -1, -4. Okay, so here we go. Yeah, so first go at this, and this is usually pretty hard to do. This is definitely thinking differently. But what I want you to get from this is that a derivative is just another function. But it's a function of, if you were to make the table, x's versus slopes. So you got to be thinking in that way. So you guys told me as x goes towards negative infinity, it gets really positive and high. It's a big number, right? The slope is a big number. Let's just go over to -4. What would you say is the slope? If I were to continue this down on this graph, what would you say the slope is right here at -4? What's the slope of the tangent line to the curve? If you were to apply a number to it, and we're not going to worry too much about the accuracy of my graph in green here, but what would you say that slope is? Is it 1? Is it 2? Is it 3? Steeper than 1, maybe? 2 or 3? 40 could be 40. It probably is. Probably is about 44. But let's just pretend it's, just 4, because my graph one goes up to 4 more. So we've got at -4, my slope is, we'll just say it's up pretty high. It's actually steeper than that, but we'll just put it up there. What about here at -1? What is my slope at -1? So I go over, it's 0. So I have a dot at -1. And then what happens next between -1 and 1? Now we're looking at between -1 and 1. How would you describe the slope of my green curve? It is negative, right? It is negative. Well, okay, if we want to, we could just do it at 0 if you want. Yeah, at 0, what would you say is the slope right here at x equals 0? Want it to be -3, okay. Some negative value, -2, 3, 4. Maybe we better do it here just the way I'm doing it. And then at x equals 1, it's back up to 0. Right here at x equals 1. So it's back up to 0, and then as it gets bigger, it takes off again. Anyways, I got a curve that looks like maybe like that. Is that a surprise to you at all? Based on our discussion earlier? Okay, what kind of function is this? No, the green one. Cubic. What kind of function is the red one? Parabola. Are you surprised? Sorry. So you're being serious? You can't tell them. Okay, sorry. So I thought you were messing with me. So y equals x cubed minus 4x is a cubic function, and the derivative is a quadratic function. And that's what we graphed here. We graphed a cubic, and then this one ended up being a quadratic. So this is an example of graphing the derivative, just getting a sketch of it, and that's all you're asked to do from the original function. And we're also going to learn how to go the other way. But you're not always given an explicit function, so you can't always just find the derivative and then graph it. You see what I'm saying? Like sometimes you're just given information about the graph. Okay. Sometimes it's the differential equation that's used as the model. That's the whole idea behind those courses of ordinary and partial differential equations that you might take in college. Is certain things in life can be modeled by a differential equation as derivatives in it. And okay, any questions on this? Right. Let's do a little bit. Let's do some more of this here. Connecting f prime to f of x. So connecting f prime of x to f of x. Suppose the graph of f prime of x is shown below. Go ahead and draw it. We're going to add this example here. So this is the graph of, if we label it, x versus slope. X versus slope. And we are asked to graph, go the other direction now. This is the graph of the derivative. Could you figure out what the original function looks like? So, let's think about it here. Go ahead and maybe draw this graph if you're going to add this example, and I can leave it up after I talk about it. It says, suppose the graph of f prime of x is shown below. So what this is it's telling me the slope, or m, equals what when x is less than -1? 2. M equals 2. And then for x greater than -1, the slope is -1. I better do this on a separate sheet, or I think it'll get confusing. I never did overlay that other one, but I think maybe remind me and I'll overlay this one. I didn't work on here. That's not good. Okay, so we got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. On this one, we've got x versus y. Okay. All right. So the breakpoint. What's the breakpoint? It looks like it's -1 here, right? It's where it fails to be differentiable there. So what we have is a slope that is constantly 2 to the left of -1. So what will that look like? We're going to have a slope. So to the left of it, so okay, right here we've got, let's just put a point right here at -1. I've got to do a slope of 2 over 1, so I would have to go down 2 and left 1, down 2 more and left 1. So to the left of x equals -1, I have a line segment with a slope of 2. So I started at 1, x equals -1. So I started at x equals -1. I did not go up right and right 1. Why did I not go up right and right 1?
Because it's a positive slope, and at that specific x value, it's
Yeah. Well, yeah, it changes. Oh, yeah, that's this part right here. So it says if f of -1 equals 0, that's probably that's where you need to start. So at -1, we need to start at 0. And then from there to the left of that, I need a slope of 2. And then to the right of it, let's go ahead.
Is it just, to the left of it because it's...
This tells me 1 point, and I need, this is called an initial value. I need this to be able to graph it. Otherwise, I don't know where on this vertical axis of x equals -1 that this thing comes together. So with that initial value, we'll learn later, it's called initial value. -1, 0 is our initial value. And then,
I get that. I don't know why it has to be like
because if I go upright and up 2 and right 1, I'm getting into the right of x equal to -1. And the slope to the right of it is -1. So to the right of this, I'm going to go just a -1 slope, so down 1, right 1. Down 1, right 1, down 1, right 1. So it kind of looks like the absolute value function, but it's not. This is a piecewise function with two different linear equations. One of them has a slope of 2, and the other one has a slope of -1. And that's what my picture would look like. If I were to overlay this on here, here's my, let's do some green. I have my dot right here at -1, 0 based on my initial value, and that's what I do first, just put that dot on there. And then to the left, I have a slope of 2, and to the right, it's a slope of down 1, right 1. So that's what it looks like overlaid on there. So as I go from left to right, we're seeing there's the slope up to -1, and then this is the slope to the right of -1. So we're going to ask you to do this in the assignment a little bit. It's hard. It's hard to get used to, but it takes like a little bit of thought. You have to ask yourself the question, first of all, what am I given? Am I given the original function f of x, or am I given f prime? And then you got to think about the scale. If I'm given f of x, I'm looking at the slopes at selected points, and then plotting x versus slope to get my f prime. And if I'm given f prime, I need an initial value. Stick a dot on there, you'll need one. And then from that initial value, what is the picture telling me about the slope to the left and to the right of that initial value? Yeah.
When you say you need a point, you mean like need as like it'll help you by your graph, or you need as it'll literally be on?
It literally has to be given to you, or you won't know where it starts.
Oh, I know. I understand that one. You mean like when you're drawing a graph, and you said put a point there, you said you need it. So that is actually part of the function.
Yes.
Okay.
Because it says it's defined.
No, I mean like when you're drawing graphs. Like,
Well, that point that they give you, and they want you to sketch what f of x looks like from the derivative, you need just to have a starting point. Otherwise, I wouldn't know where to put that.
I understand that. I'm just saying like when you're drawing like a travel, you're probably there you go. What I'm saying is actually like like when we're drawing limits points, it's like that's important to the actual function.
Yeah.
When we're
Wait,
drawing,
on these, that initial point is important. Yes, to make sure it's clear right now. All right, here we go. So suppose the graph of f prime. So I'm giving you guys f prime again. This is just the graph f of x equals x. You already know where we're going. Yeah. So this is f prime. I mean, this is just a clip from the graphing calculators. You know, it's not a function that can't be modeled by something explicit. So this is actually y equals x. I can tell by looking at the slope and where it goes through the y-intercept. It's y equals x, or f of x equals x. So this is the graph f prime. And what we're going to do is I need to see that. There it is. Suppose we are going to sketch what f of x could look like. All right, so I'm going to start out by plotting the point that they gave us. It says if f of 0 equals 1, so f of 0 equals 1 would be that point, 0, 1. Sketch what f of x could look like. So remember, this up here is x versus slope. X versus slope. So if I'm going to draw f of x from this, let's look at what's happening maybe right here. At -1, what is the slope of the tangent line to my curve? It's -1. Yeah, it's exactly it's exactly -1. So at -1, remember this is slope. You gotta get this in your brain. This is slope. So instead of a y coordinate, it's telling me the slope of the little tangent line. Now what I'm going to draw is at x equals -1, I'm going to draw a little what we call tangent line with a slope of -1. So it's going to look kind of like that. And here it does help if you understand the relationship between linear and quadratic functions. But I'm going to draw a little slope right there. And then, like down here at, say at -2, what happens to the slope? Is it getting steeper negative or?
Yeah.
-2. So at -2, it's even steeper. And I'm knowing to put these up above it because I have an idea of where we're headed. But you have a slope that's going from, if you think big picture, it's going from really steep negative all the way down to 0 slope, and then it's going to turn around and start getting positive and more steeper and steeper. What does that sound like? -0, positive, right? So if you kind of look at it big picture first, it might help you to have a better idea. So what about at x equals 1? What's the slope here? 1. And then at x equals 2, it's getting even steeper. So I have a parabola that looks like that. So you're going to, and hopefully we don't need to do this point by point. You're going to put your initial value on there. You're going to see that it goes from really steep negative on the left, eventually hits 0 and levels out, and then goes to really steep positive on the right. Last one here. I just have one more for you. Suppose, hey guys, suppose the graph of f prime is shown below. So this is our, I'm turning it around on you a little bit. Okay? This is f prime, and it's the absolute value graph, and we don't know what the absolute values, like that graph, is it the derivative of what function? Like we don't know that. Like on the previous one, some of you knew. A linear function has, if you go backwards, it's quadratic, right? So now we don't know that. So how would you handle this? What would we do? So we've got on here. So we're graphing x versus y. We know that we've got a point at 0, -1. So we got a point at 0, -1. What's this telling me about slope in general to the left of that point 0, -1? What's happening here? So what's the curve doing? It is a curve. The curve doing.
Yeah.
So remember, this is x versus slope. So when x is super negative, what's the slope? Is it? And we're not looking at the slope of this curve. It's really big positive number, right? So it's going from really big positive number to smaller and smaller. So it's starting up like this, really steep. So a really big positive number, actually like this. So really steep. And then as it gets closer to this guy, it starts to level out. So you tell me, should I be bringing my curve in from the top of the red dot, or the dot at 0, -1? Or from the left of the dot at 0 to -1? So it's starting really steep, and then it's gradually going like this. Yeah, it's got to be below it, right? Because what's it going to do? What's it going to do at 0, -1? At x equals 0, this tells me the slope is 0. So at x equals 0, the slope is 0. So I know I've got a little horizontal line here. Okay, like that. So yeah, it's going from steep, steep, not so steep, and then boom, hits 0, and then what does it do? then it takes off, and does it turn to negative or does it go back to positive? So what curve do I have?
You have the cubic.
Looks like a cubic, yeah. What it looks like. Good question. Think about that.
Because it's not zero ever at that point. The slope is never zero. Okay, so it's not
actually.
Oh, because so it doesn't have a maximum.
It's like a piecewise graph.
It is. It would be like two little piecewise parabolas put together.
Is this a continuous function?
Is it a continuous function? This one, it is. We're going to learn that if it's differentiable at every point, then it is continuous. So yes, it is. But we haven't talked about that yet. That's a theorem. But so guys, did you catch that? Good question. Is this really a cubic? Even though it looks like a cubic, is it really a cubic? No. As a matter of fact, the argument that it's two piecewise quadratics put together makes more sense, because a quadratic derivative will be a line. So, and that's a better description. But it's a curve that looks like that. Okay, we graphed it from this, and this is going to be the hardest part of your homework. So, is I think being able to get the graph of f from f prime. I think it's easier going the other direction, but see what you think. So the assignment's in there. Any other questions on this? I'm going to have you do some practice problems here now.